Welcome to Velocity and Luminance Adaptive Rasterization with Variable Rate Shading Tier 2 running on Intel Arc Graphics. Today we're going to talk about the basics of VRS with DirectX 12. We'll also talk about a specific implementation we did that we call VALAR. It's Velocity and Luminance Adaptive Rasterization. We'll go into the implementation details, some optimizations we did, as well as some quality analysis. And then finally, we'll have a resource section, and this is our legal notices and disclaimers slide. This is our acknowledgement slide. There's been a lot of people that have helped us along the way, and we wanted to make sure that we recognized everyone that made contributions. So next up, we'll talk a little bit about us. I'm Marissa Dubois. I'm a senior graphics software engineer at Intel. I've worked here for the past 5 years, and in that time, I've been focused on games enabling and performance optimizations. Most notably, I enabled VRS Tier 1 in Unreal Engine, as well as Chivalry 2. And in my spare time, I am a Lego electronics maker, and my work has been featured on multiple Lego advertisements.
Thanks, Marissa. And my name is Adam Lake. I've been at Intel a little over 20 years, and my current role is at the intersection of the hardware and the software. I work with game developers and the spec owners out in the industry to bring those requirements into our hardware team and translate those into hardware requirements. And similarly, I take new hardware features and work with game developers to ensure that they can use them in their next generation content and educate them about how to use them best on our hardware. I have a few examples most recently on the slide, mostly focused around variable rate shading. I also want to mention I worked as an Intel representative in Kronos for OpenCL 1.2 and 2.0. So with that introduction, I want to lay the foundation for some of the specifics that Marissa is going to talk about in her portion of the talk by laying out the spec and kind of teaching what variable rate shading is and where we might want to use it. So the first question we want to ask is why we might want to use variable rate shading. The original motivation for this, and we observed this back in around 2014, 2015 timeframe, is that the display resolution is growing faster than the pixel throughput that we can push through our GPUs. So we saw that we were moving from 1080p up through 4K, and then eventually we would have 8K resolution. And we needed to find a way to vary our shading rate and put pixels where they matter the most. This is important on low-end or integrated and mainstream graphics GPUs whenever we're trying to hit specific frame rate targets. But it's also useful on high-end GPUs where we're trying to reclaim those execution resources and use them, where the customer is most likely to appreciate that visual impact. So we might want to take the reclaimed time back by using variable rate shading to put a higher end effect that we might not be able to do on integrated or mainstream for our high-end experience. The other thing that I want to mention is VRS is often compared to dynamic resolution rendering. And for us, this isn't really an either-or conversation. We think of VRS as something that's very precisely being able to be used to control the pixel shading invocations on our GPU. Dynamic resolution rendering is a more heavy hammer where we aren't controlling just the pixel shader invocations, but we're also controlling our depth, stencil, and coverage buffers. So those are all being reduced to a smaller resolution. And the end result is a little bit more blockiness at the equivalent VRS shading rate. And you can see that as an example in the image on the right side of this slide. So I wanted to mention a few games that are actually taking advantage of VRS today. This is a very kind of exciting slide for me to present because the first time we started talking about this back in 2019, we had to say, like, here's this great tech, but no one's really taking advantage of it yet, so we look forward to what people are going to do. And since then, there's been a number of titles, and I've included some of those on this slide. These links are all live. You can go read the articles where they speak to how they've used VRS in these examples. And the key takeaway here is in all these cases, they're able to increase the performance by between 10 and 30%, depending on how aggressive they use VRS, and have no visual degradation to the experience from the user's perspective. So we have a whole list of references in the back of our talk in a references slide, but the ones that speak directly to what we are talking about today are listed on this slide. And I want to draw your attention to this paper by Li Yang and NVIDIA Research. We gave a talk back in 2019 where we had just recently read this paper, and I was pretty excited about trying to do an implementation of this. And what the talk is that you're going to see today when we talk about VALAR is an implementation of this paper. So back to talking about some of the fundamentals about VRS, I want to speak about what a coarse pixel actually is. Over on the right-hand side, we have pictures of the different coarse pixel sizes. And if I just use the 2x2 example, you can see that what we're doing is that red dot denotes where we're actually doing the shading. So this is where our texture UVs would come from, etc. After we calculate that result of the coarse pixel, we propagate or broadcast that result to the fine pixels that make that coarse pixel. I want to mention also that the default implementation is required to support the box in green, or the 1x1, 2x1, 1x2, and 2x2 shading rates. But Intel also supports 2x4, 4x2, and 4x4. And there's a capability bit that you can look to query for whether they support, an implementation supports these additional shading rates or not. So the next thing I want to talk about is where we might use VRS. We did a talk back at SIGGRAPH in 2019 where we went into a lot of detail about the use cases here. So I encourage you to look at that reference if you want to see more of the analysis that we did. But this slide is basically a summary of that presentation. So a few things we've learned and we've talked about before are integrating VRS into our level of detail system. Examples of where you might use this if objects are moving quickly that are far away or in the periphery of the scene, these might be candidates for VRS. Other times are when objects are in fog, particles, and smoke. Basically any atmospheric effect where you might have a blur being applied to the object anyway, or a distortion that is going to impact the quality, you can go ahead and use a more aggressive shading rate. This picture in the upper right kind of shows this fog effect, and we did a little user study, and the key takeaway was this scenario had some spheres rotating through, and those back blue ones represent where they were being reduced to a 4x4 shading rate versus 2x2. And if there was no fog applied, you actually could discern 4x4 coarse pixels, but 2x2 was fine. But then with the addition of fog, even 4x4 was able to go into that background and not be perceived by the user. So this second area is whenever objects are known to undergo blur from the lens or motion. So you see an example of this child jumping on the right-hand side, and you can see the pixels that are near the feet or the hands. Those are going to be blurred, and you can determine this with your velocity buffers or your motion vectors that are usually part of your rendering pipeline. And if you know those pixels are going to be under a high velocity, you can go ahead and be more aggressive with your coarse pixel shading rate. The final point that I want to make is about whenever you have slowly varying shading parameters, things like diffuse shading or ambient occlusion, these passes are also good candidates to apply a reduced shading rate where you can get that performance back. An example of this Olaf model in the lower right, you can see, a lot of the pixels have the same color. It's not going to matter if you reduce the number of indications there. They're getting the same shaded result. A final point is where we're using VRS to save power. Recently, Valve actually published an article, or there's an article about Valve's implementation, and I link to it here, where they mention they use VRS on the Steam Deck. And the context there is the observation that the displays on a small LCD that's part of their mobile device has more pixels there that can be discerned by the human eye at a normal viewing distance. So the idea there is just go ahead and, there's no need to shade those pixels. You're over shading relative to what your user is going to perceive. So reduce your shading rate and you can use that to save power. Another thing that I want to speak to is how the variable rate shading specification in DX distinguishes between different hardware implementations. So there's tier 1 and tier 2 hardware. Tier 1 hardware allows us to change the shading rate per draw call. And this is what Intel implemented on Ice Lake and Tiger Lake GPUs. Tier 2, which is introduced with Intel's Alchemist GPUs, is where we can, in addition to changing the shading rate per draw call, we can also change the shading rate per image tile or per primitive. On the right-hand side of the slide, I have an example of an overlay of the shading rate on a per tile basis. And this is just an early prototype of our implementation. So each tile gets a different shading rate, and that's denoted by the color in the slide. I mentioned also per primitive. In Tier 2, we haven't done much work with that yet, but it is an area to explore in the future. The other thing that's part of Tier 2 is this additional feature called shader combiners, and I'll talk more about that on the next slide. The final point I want to make is there's a whole, there's a significant number of additional details if you want to use VRS, and I referenced the Microsoft spec here. If you want to get more details on how it interacts with MSAA, conservative rasterization, etc., I'd encourage you to read the spec. It's very, very well done, very complete. So I mentioned on the previous slide that I wanted to talk a little bit about shading rate combiners, which is part of VRS Tier 2. And over on the left here, you see this represented as an equation, where effectively what we're doing is we're needing to determine who's the winner between per draw call and per primitive, and that goes into combiner 1. The output of that is then submitted to combiner 2, which resolves basically picks a winner between the output of combiner 1's result and per tile. So on the right-hand side here, I show this visually where you can see A and B going into combiner 1. That output is submitted to combiner 2, which is merged with per image tile to compute the final shading rate. And the combiners have 5 different operators they can apply. And they're pretty, I think, intuitive about what you might expect in an implementation. You can pass through the value. You can override it with what's incoming on edge B from the image on the right-hand side. You can also pick higher or lower quality on a per axis basis. And I mean, by per axis, I mean the x-axis or the y-axis. You set the shading rates on those 2 directions independently. And the final operator that the combiners can implement is the sum operator. These can be a bit confusing at first. And one idea is to play around with these with our sample, maybe add some code and do some experimentations if you want to get a better feel for how these work together. So in addition to the shading rate combiners, there's an additional set of capability queries in DirectX 12. You have to ask a few different questions whenever you're implementing your VRS implementation. A couple of these questions. For example, does the implementation support an extended set of shading rates? Can you support a different shading rate per primitive per viewport? Third, is the sum combiner supported? And fourth, can mesh shading and variable rate shading be used together? And I'm glad to support today that Intel Alchemist supports all of these capabilities. You'll report true on them if you query the runtime of our driver. There's a couple of other features here that I've already spoken to you about. One is, you need to know whether you're Tier 1 or Tier 2, and the shading rate tile size, whether it's 8x8 or 16x16. And these are the values that Intel Alchemist is going to return. So now that I've spoken about some of these different capabilities and things you need to be aware of, especially during initialization, I want to put these all together in pseudocode to understand what we need to do during that initialization step and what we're going to do during runtime. And Marissa, whenever she does her portion of the talk, she's going to actually show some code samples of this in our implementation. So the things you want to do at runtime is first query for VRS support, whether you support Tier 1 or Tier 2. The second is to query for the optional shading rates and capabilities of the hardware. Third is you're going to want to create a VRS shading rate image. And that image is going to be, in our case, 1/8 the frame render target size in both width and height. The fourth thing is to set up your VRS shader combiners, as we talked about on the previous slide. That's the initialization step. And then we go to the runtime steps. And the way you modify your render loop is you're going to do a few different steps. First, every frame you're going to use in our implementation, or in our example, we take the frame that was rendered from the previous render, and we use that as input to determine our error metric. And based on an error metric, we're going to set per tile our VRS shading rate image. The next thing is we're going to update, signal an update that our shading rate image is changed on the command list. And the third thing is to issue our draw calls. Now I show this very simple render loop here in pseudocode, but it's important to also know that if you want to switch shader combiners between draw calls or change a shading rate image per draw call, you can be very aggressive in your use of these other APIs. You just want to be sensitive to the performance implications of switching those rates or switching the combiners multiple times per frame. Final point I want to make is VRS is not a panacea. It's very good when we're pixel shader bound. Remember, we're preserving depth and stencil at full render target resolution, but we're saving some of our pixel shader bandwidth to be put in places that have the highest impact for the game player. However, VRS does not help when we have areas or render calls where we're vertex shader or geometry bound. Also, specular surfaces can have a problem, and we and other people that have done implementations have spoken to this point. And we, a couple different ideas, including ours, was to modify the roughness parameter whenever you're using, whenever you have highly specular surfaces, reduce the roughness so that you can smooth out where you might have flickering because of if you had too coarse of pixels. Another area that it doesn't help is when triangles are getting smaller and when they're approaching or beyond a coarse pixel size. Obviously, the setup time, etc., is going to dominate the time of shading. There's a recent paper on software rasterization with VRS, and I reference that here. And I encourage you to look at this paper because the Filmic World's it's a blog article, and he goes into the details of when hardware wins and when software wins. It's a great article. I encourage you to take a look at that. So I'm going to finish up just speaking about a couple points of future work. We've listed a number of things here, but just to hit a couple things we want to do here. One is we want to be able to compute the VRS shading rate via asynchronous compute. We're kind of setting things up for that, but we just haven't gotten a chance to implement that yet. Another thing we want to look at is to evaluate the quality and performance trade-offs of other error metrics. One example is the Xbox team's Martin Fuller used a Sobel edge detector instead of what we used, which was a mean squared error. And it might be useful to do some comparison of like quality versus performance of using a simpler error metric. I also mentioned previously some of the exciting work that's going on with software VRS, and I referenced two of those articles here. So to conclude, I'm looking forward to what the developer community is going to do with VRS on our GPUs, and we look forward to working with you to take advantage of VRS. So with that said, I'm going to transition over to Marissa, who's going to talk about our implementation and how we combined VRS Tier 2, Microsoft's DX12 MiniEngine, and the recent graphics research that I referenced to build a fully open source demo on Intel Alchemist.
So next up, we're going to talk about the implementation details of our VALAR implementation. And first off, this is a new feature on our next generation Intel Alchemist GPU. It's Microsoft DirectX 12 compatible. So for our implementation, we have an 8x8 tile size, and this, essentially represents 64 pixels on the main render target. If you look at the diagram in the top right, you can see a representation of the tile. This tile can be broken down into two 4x4 coarse pixels or four 4x4 coarse pixels. And these basically reduce down to a single pixel in the shading rate buffer. The shading rate buffer format that we use is R8 uint, and the shading rate buffer size is 1/8 of the render target size. So as Adam mentioned, the first thing that we need to do is query the hardware details to make sure that VRS Tier 1 and Tier 2 are supported. We do this using the D3D12 option 6 structure. This structure returns the shading rate tier, whether or not the additional shading rates are supported, as well as the shading rate tile size. And then optionally, we can use the D3D12 options 10 struct to get the variable rate shading sum combiner support, as well as the mesh shader per primitive support. So once we've detected the hardware capabilities, the next thing we need to do is actually set our shading rate buffer as well as our shading rate combiners. We do this with the DirectX 12 API. We use the ID3D12 graphics command list 5 object. This exposes the VRS API through the RSSet shading rate function. This function lets us set a global shading rate as well as the shading rate combiners. And then next, to get the VRS buffer attached to the pipeline, we call RSSet shading rate image. This takes the R8UN shading rate buffer. And at this point, we can configure our combiners to work for our algorithm. And in this case, we use the pass-through and override combiners. And these are the combiners needed in order for our algorithm to work. So what is velocity and luminance adaptive rasterization? It's a technique that's based on the adaptive shading paper by Li Yang in 2019. Essentially what it does is computes the mean squared error of an individual tile. And it does this in both the X and Y axis. And then we're able to compute what's called a just noticeable difference. And we use this just noticeable difference to compare to the mean squared error and determine the shading rate tile size. Now there's a few key parameters that are passed into the shader in order to get everything to work, and these are artist tunable. So the first and primary input parameter is the sensitivity threshold. This controls the full rate and half rate shading. Next, we have the K value. This K value is the quarter rate shading modifier and will control how aggressive the 4x4 shading rates are applied to the shading rate buffer. Finally, there's another parameter called environmental luminance. This is essentially an additive global illumination value, and it can be useful in areas of low light or low brightness. So to get this to work, it does require a little bit of modifications to the rendering pipeline. So first we start with the frame start. At that point, we set a shading rate buffer where everything is set as 1 by 1. We render the pass that we want to render using our VALAR compute pass. We can also optionally render the motion vectors in the velocity pass and then pass those into the compute pass. The VALAR compute pass then takes that data, does the mean squared error and just noticeable difference calculation, and then saves out the shading rate buffer and stores it for the next frame. And then the frame ends and it loops back to the beginning. So there's a single compute context initialization. And this initialization takes 3 UAVs, the shading rate buffer, the render target buffer, as well as the optional velocity buffer. And then we pass in the tunable parameters such as the shading rate, sensitivity threshold, environment luminance, and K values. Now the key thing here, when we dispatch our shader, we actually dispatch it at the size of our shading rate buffer. Typically, this would be 1/8 of the render target size. And then within the shader itself, we set our tile size as the number of threads. So we pass, for Intel hardware, we pass 8 by 8 into the number of threads. So in our implementation, we actually have 3 different flavors of the VALAR compute shader. But essentially, they are all broken down into 2 main phases. There is a parallel phase where we compute the mean squared error of the luminance, and we can also compute the minimum tile velocity. And then there's, after that completes, there's a serial phase, and the serial phase basically averages our values, computes the just noticeable difference, and then writes our shading rates out to our shading rate buffer. Now, originally, our unoptimized pass was sort of a naive implementation to do luminance summation. It turned out to be a bottleneck, so we looked for ways to optimize this shader. We'll go into more depth on these optimizations later in the presentation, but just at a high level, The first attempt we did was shared local memory plus wave intrinsics. This gave us about a 4x performance boost over the unoptimized version. But we also wanted to experiment with atomics, so we combined shared local memory with wave intrinsics and atomics. This gave us about roughly the same performance gains as the shared local memory and wave intrinsics. But there are a couple of trade-offs like reduced group shared memory and a little bit slightly cleaner code. So we have all three of these in the demo application so that you can take a look and understand our optimization approaches. Okay, so the way that the shader actually computes the shading rate buffer, if you look at the top right, we start with a full color image. We convert this image into linear RGB and then convert that into luminance. At that point, we essentially have a grayscale image, and from that grayscale image, we are able to compute the Luma differences per tile in both the X and Y axis. And we use the wave active sum in order to speed up the process. At the same time, we can compute the minimum velocity for the tile if the velocity pass has been enabled. So next up, we compute the just noticeable difference and the mean squared error. We do this by dividing the render target into 8x8 tiles. And then for each 8x8 tile, we compute the average luminance. This essentially down-reses the original image. So next we compute the just noticeable difference threshold. We do this by scaling the average tile luminance plus the environmental luminance by the sensitivity threshold. Once we have the just noticeable difference threshold, we compute the mean squared error in both the X and Y axis, and we just take the square root of the average tile luminance in each axis. So now that we have our just noticeable difference and mean squared error, what we can do is compute the shading rates per tile. And at this point, we can introduce an optional velocity error modifier. And this was described in the Li Yang paper in 2019. We will talk about some optimizations we did for this equation, but essentially it just is a modifier to the mean squared error. And then we take the modifier and we scale the average error in both the X and Y axis. And then we have logic to compare it to the just noticeable difference threshold, which results in our 1x shading rates, 2x shading rates, and 4x shading rates per axis. And you can see this represented in the top right, where we have 1x, 2x, and 4x shading rates represented in green, red, and transparent. But we can combine those per axis shading rates together once we've done the just noticeable differencing for each axis. And this gives us our full range of shading rates from 1x1 all the way to 4x4. And then finally, we just write these out to our buffer and store them for the next frame. So what we get from that is a content-dependent performance speedup. We have three modes that we test with. We have a quality mode, a balance mode, and a performance mode. The only difference between these modes is that they each have a different sensitivity threshold, where quality mode is 0.25, balance mode is 0.5, and performance mode is 0.75. And what we see as we increase the sensitivity threshold, we see a reduction in pixel shader invocations, ranging from about 27% to about 88% overall reduction. This results in a GPU time speedup across all of our test cases, ranging from a 1.05x speedup to a 1.12x speedup in the best case scenarios. So we did an additional experiment. We actually found that there's two modes to do Luma differences. Both of these modes are based off of what's called Weber's contrast law. And the first mode we have is basically an approximation, where we just take the difference between neighboring pixels and then essentially average them together. But we have a more precise method. We call it the Weber-Fechner Luma differences. We essentially compute a brightness sensitivity based on a 3x3 grid of neighbor pixels. And then finally, we take the difference and divide it by the minimum luminance of the neighbor pixels and then add the brightness sensitivity to that. And so what this results in is the approximate Luma speedups. We have a 1.05 to a 1.12 speedup. We can show that we can result in higher performance, but also lower quality. But when we use the the Weber-Fechner Luma speedups, what we see is a speed up of 1.03 to 1.09. So we have slightly lower performance, but it does result in higher quality. And we'll go into more detail on the quality trade-offs in a later section. Next up, we'll have Adam Lake talk about the performance optimizations we did, and he'll go into more detail on the specifics of each.
Thanks, Marissa. So I'm going to go ahead and talk a little bit more about our optimizations. And for these, we focused on the average tiled Luma value, as well as the just noticeable differences in X and Y to set the shading rate. To do this, we looked at 3 different features to take advantage of in compute shaders. One was the use of wave intrinsics. The second, what we used is what's called group shared memory in HLSL, or shared local memory, which we refer to as SLM on Intel hardware. And the third thing is the leverage of atomics on SLM. So the first slide here shows our basic implementation. And what we did here is after conversion of the values into luminance values, we loaded these values into SLM. And then on the bottom right of the slide, you see a for loop where we basically walk these values to get the totals that are used to calculate the averages. You can see this is just a simple for loop that walks all of these values of the tile. In Intel's case, it's an 8x8 tile, so there's 64 total values. And this works fine. It's functionally correct, and it looks pretty good. However, we wanted to know if we could do a little better in terms of performance. So the first thing we did is we looked at using wave intrinsics. And the basic way that wave intrinsics work is your thread group is broken down to a set of waves. Those waves are typically SIMD size. And in our case, again, back to the 8x8 tile, we have 64 values on Intel, and we decompose those into 4 waves of SIMD 16 width for each wave. In SLM, we put basically a bin for every value for each wave, and we sum the values for each wave into that bin, and then we do an execution of memory barrier and wait until all of those values have posted. And then we go ahead and walk those to compute the tile's averages for the tile. So we're basically doing a for loop over a much smaller group of values. And this provided a pretty nice performance speed up. We wanted to then see if atomics could do any better. And that's the implementation you see on the right-hand side of this slide, where we used an interlocked add, and we continue to use our wave active sum. One of the advantages to this approach was we didn't need to use as much shared local memory because we were just using one SLM location per wave of our thread group. The other subtlety here is there is no FP32 atomic for SLM in shader model 6.0. So instead we did a conversion to an integer, and we use that integer to then basically decode it whenever we're computing the sums at the end of the pixel shader. The resolution here for us was fine when we did our implementation. So the performance of these is shown on this slide. So we used 1.0 as a normalized, we'll call it the for loop or the base implementation, and the 2 attempts at optimization are the green and the blue. You can see that both of these are about a 4x speed up, and all of these are on the order of microseconds in time. So they're all very fast, and we're pretty satisfied where this optimization left us. There's probably some more that you could do, and we're still open to that. But we kind of stopped here. We felt like we got this fast enough. We got kind of a low-hanging fruit, and we wanted to move on and do some other things. It was interesting that the atomics were performing slightly slower than not using them. We didn't really pursue, deep dive into that any farther, but it was interesting to see the performance was about the same. The next optimization that we wanted to look at was related to the observation that you can use a less aggressive shading rate whenever your objects are under motion. And in Li Yang's paper, he derives these functions on the left-hand side that effectively allow you to, there are like scale factors on the mean squared error metrics that you're comparing against the just noticeable difference threshold. And so they allow you to adjust the metric. And these are the right equations. It's functionally correct. But I was a bit concerned, if you look at these functions, they're raising things to a power and there's some divisions. And I just wondered if we could do something that was a little bit higher performance. One of the reasons for this is when we look at our GPU, we don't have as many execution resources when we're raising things to a power, for example. I show down at the bottom, Tiger Lake is basically able to compute that type of operation at around 2 ops per clock per EU versus the ability to have 8 fmads. So the basic idea here is if I can turn these into mads instead of raising things to a power or the division, then I can get better performance. And while I want to also mention, this isn't the crux problem in the performance of this kernel. We know it's I/O bound primarily, but still freeing up those ALU resources should provide us a small performance increase. But I was also trying to think about the future whenever we were going to implement this in an asynchronous compute mode, where another thread might want to take advantage of those execution resources. And by freeing those up, we get a reduced latency and overall performance for our application. So on this slide, I show these linear approximations that we used on the right-hand side. And you can see the original equations are in orange and our linear approximation is in blue. And I have the pseudocode for this on the left-hand side of the slide. And these are all in the source code that we're providing to developers. And you can experiment with these to see if they suit your needs, or if you want to adjust the linear equations because you're not satisfied. That's easy enough to do. The code's right there. I want to mention, though, that we kind of think that the right way to do some of those modifications is to adjust the just noticeable difference threshold parameter. We think of this as kind of like a global control. So the inputs to that are adjustable via the UI and the interface for our demo. And kind of think that that might be the right way to go. But if for some reason you don't like this, feel free to use the closed form function. You're still going to get good performance and an accurate result, of course. So we saw a few microseconds in speed up of this, and we do think every millisecond counts, but we understand that you might prefer the closed form function. So with that, I'm going to now turn it over to Marissa, who's going to talk about our quality analysis of our implementation.
So yeah, we'll talk about the quality analysis that we did. Essentially, there is a quality trade-off with the performance gains with VRS, but we think that these are minimal, and we'll go through our analysis process to try to prove this. So basically what we did is we compared 2 different error metrics for measuring quality. The first one we chose was Image Magic, and this produces a PSNR value, also known as peak signal to noise ratio. But we know that this isn't necessarily a good approximation for human perceptibility. So NVIDIA has released a paper on a technique called FLIP, which will produce a mean error value. And we think that this one is actually going to be more accurate to what the human eye can see. And then within our application, we basically have 3 test scenes that we compared. And we compared the same 3 sensitivity thresholds that we discussed earlier, the quality, balance, and performance modes. So this is a 4K image rendered using the balanced mode. And I want you to pay attention to sort of the area that's in the red box. This does have VRS Tier 2 applied, and it should look pretty much like the original Sponza scene that you might expect to see. Now, if we look at this with the PSNR diff, it basically is just a raw numerical comparison that produces a decibel value. And everywhere you see a red dot, it means that the image has changed slightly. So in the red box, you might see, there are a lot of red dots, but there are also a lot of areas that are, have a lot of white dots, and the white dots indicate that, quality is being preserved in those places. Now, if we look at Flip will produce a histogram that's based on the human perceptibility metrics. And if we look in the red box, we can see that a lot of the stuff within that region is rendered at a really dark color, which means there's very little change that's perceptible to the user. You will notice that there are other bright purple spots. These are the areas that have changed more, but we think we're still retaining quality in a lot of these spaces. But if we look at the actual overlay of where we're doing our shading rates, you can see a lot of those areas that had the color preserved or the quality preserved. We were actually rendering those at 4x4 or even 2x4 and 4x2, and we were still able to maintain a very high quality in those regions. But we have data that also shows this, and we have data from both the PSNR measurements we took, as well as the flip measurements we took. And again, PSNR is okay to measure quality differences, but it might not really tell the whole story because some of that information might not be perceptible. Now, what we do show is as the sensitivity threshold increases, quality does decrease as we would expect, but it doesn't, fully degrade the image. Now, when we look at the flip values, we can see that these ranges are a lot more constrained. And as we increase the sensitivity threshold, we are still losing quality. But in terms of perceptibility, it's very minimal. So, our worst case is we lose about 6% quality. Our best case is we lose about 2% quality. We still maintain a very high quality image by using all of these modes. But we've also compared the Weber-Fechner luminance to the approximated Luma differencing that we described earlier. And what we do see here is that the Weber-Fechner does preserve more quality, especially as the sensitivity threshold increases towards 1. When it's closer to the 0, they're pretty much on par with each other. So you might want to consider having a way to switch between modes as your sensitivity threshold increases. And we can actually visualize this using the histograms produced by Flip. And so what you see in the top row is our approximated Luma differences for quality, balanced, and performance mode compared to the Weber-Fechner Luma differences in the bottom row. And in all the cases, the Weber-Fechner Luma differences reduce in a lower error accumulation. It's pretty close in the quality section. If you look at the blue arrows, they're pretty much at about 0.2, even though the approximate might, accumulate a little bit more error. But if we get over to the performance mode, we can actually start seeing a big difference here. And what we notice is the approximated mode, we start forming more of a bell curve where we've added a lot more error. But looking at the Weber-Fechner one, the bell curve is still very clustered to the left and very similar to the other two modes that we have. So we also have a video of a fly-through of the demo application, and this is rendered at 2K. And we'll compare, the first section will compare the technique without the motion vectors, and then the second section will compare the technique with the motion vectors. So here we go. And as you can see, we're flying through. We do have the overlay on here, but it will turn off right at this point, so you can kind of get an idea of what the image would look like to the naked eye. And, it does maintain high visual quality. And then next we switch the same with the motion vectors applied. And what you'll notice is that the 4x4 shading rates are much more aggressive. They do concentrate in the periphery of the screen. And you'll see that again when the overlay comes back on. You can see that it kind of has some concentric rings of where it tries to preserve quality, where the user's eye would be drawn. So finally, we have a list of resources that go along with this presentation. These include our MiniEngine samples, as well as a white paper that goes along with the sample code and this presentation. And then we've also included links to the quality analysis tools that we used, including Flip, iCat, and ImageMagick. And then we have a full set of references that we used in our research and in this presentation. Thank you for watching.